Welcome, Vasily. And Vasily is in Lund, in Sweden.
Yes, thank you very much. Can you see my screen?
Yes.
Okay, perfect. Okay, thank you very much. It is a great pleasure to be a part of this conference. So I will talk about, the title of my talk is Linear Dissipative Force as a result of discrete time collisions. And actually, this problem was proposed by Vadim Alexandrovich when I was his student at Mehmat. So yes, let's start. Here in this talk, I will consider two models. The first model is the movement of particle under the influence of external force and friction, or like we call in this talk we call dissipative force as friction. So it is one model, and yes, I should say here that we are talking here only for one-dimensional case. So particle means like the point which goes in the real line. And another model is again movement of the same particle, which is acted upon by the same external force, but in this model, we don't have friction force, but instead we have collisions with other particles, which have lighter masses comparing to the main particle. And the question here is, when are this model equivalent in some sense? So can we describe the friction force through collisions with small particles? And this problem refers us to George Stokes' paper from 1850. He introduced the frictional force, which is also called Stokes' drag, FD. And this force can be described as the following, as this equation. And in this equation, V is the velocity of the particle. And yes, in this problem, we assume that the particle is just a three-dimensional. No, this is just a ball in three-dimensional space with radii r, and this particle goes through some fluid, and this fluid has dynamic viscosity mu, and everything multiplied by 6 times pi. So in this case, 6 times pi times mu and r, this is just a constant, which is multiplied by the velocity of particles. So this is exactly the force which is linear dependent on the velocity of particle. And actually, this force works only when we have laminar flow with small Reynolds numbers. And when it is small, then we can approximate this force as a linear dependent force. But if Reynolds numbers becomes bigger, then this force will be different. So, for example, it could depend on the square of velocity, not only linearly dependent. For example, if we go through the air and there is a speed of sound, and if our velocity is less than speed of sound, then the drag force or the friction force will be linear. But if our velocity is greater than speed of sound, then the friction, because of this flow is not laminar in this case, it will be turbulent flow. And in this case, there are some terms which is v squared times some constants and so on. So we consider just laminar flow here. Okay, we start with initial conditions. So we assume that our particle So the movement is just a coordinate x0 and the velocity of particle v0 in R2. And we start at time 0, and we call our particle the main particle. Assume also that the mass of the main particle is 1, because otherwise we can just divide everything by the mass of the main particle, and the coordinate x0 is greater than 0. Here we have strict inequality because in future, when we consider some specific case, we need that x0 should be greater than 0. And there is an external force which could depend on the place x in the line. Also, it could depend on time. So there is an external force. Okay, so consider the first model when there is a friction force. So we just take some constant A and fix it, and then we can describe the movement of particles through the following differential equation. So this is just the sum of all forces which is acted to the particle. And this term, this is just acceleration, and we should multiply this by mass, but as I said, the mass is equal to, of the main particle is equal to 1. And we can rewrite this equation through the system of these equations. So here minus A times V represents friction force. And we want to consider this problem with different forces, with different external force F, with different cases. Okay, and this is the model when we have the movement with friction, and the other model when we have collisions. So in this case, we denote it as x tilde v tilde. We have the same initial conditions as in model with friction. Also, at time t1, t2, and so on, our main particle collides with other particles which has masses mn, of course, all of them less than 1. And this particle has velocities wn. But between collisions, our particle goes with the following law. So only this force, which is the same as in friction model, we have the same force. But in this case, we don't have the term minus AV. So we don't have, no, not friction. This is external force, but we don't have friction force minus AV. And we assume that these collisions are elastic. So in this case, we need to define this auxiliary term alpha n. And we said that, yeah, also we should say that the trajectory x is continuous function and v tilde, x tilde is continuous function and v tilde is right continuous function. So at the moment of collisions, our velocity jumps to some other numbers, and it jumps according to the equality 4. So with this alpha n, we can define how the velocity changes after collision. Okay, and let's consider some results for some specific cases of external force and parameters. So firstly, like the most simple problem which could appear here is just consider the force, which is just a constant, external force is constant. Then the masses of the other particles, of small particles, they are the same, is equal to m, which is less than 1. Also, velocities of the other particles are the same and less than f over a. Recall that a, this is constant with this friction force. And also moments, like the time between collisions, tau k, is equal to the same constant tau, which is greater than 0. So in this simple model, there is a theorem that it tells us that velocities v and v tilde in both models with friction and model with collision are asymptotically equivalent in the sense that the limit of the velocity in the model with friction is equal to limit velocities with the model with collisions at time moments tk, if and only if there is this condition 6. So in this case, we should take time tau between collisions. It should be it should have exactly this form. And furthermore, these limits, these velocities are finite, and this limit is equal to f over a. So, like, if we fix m and w and f and a, so we have to take this parameter tau, which is equal to this this number. So this is just necessary and sufficient condition for asymptotically equivalence. Okay. After that, we could ask ourselves, what if this time between collisions are random, for example? Okay, we sorry. Firstly, I should mention here that if this mass of particles are really small, like goes to 0, then the order of this time tau between collisions are also of order m. So the masses and the time between collisions has the same order here. Okay, and if we have the same conditions as before, but instead of a constant time between collision, if we take IID positive random variables with finite second moment, then again we have asymptotical equivalence, but in this case, of course, because V tilde is random now, here we take expectation. So basically, because yes, we take expectation, and we have a condition here that expectation of tau should have the same form as before. So actually nothing special here, because like to prove this fact, we just take the proof of previous theorem, and instead of tau, we just take expectation. But what is interesting here is that here we can compute expectation of square of difference between velocities, and this difference is equal to this quantity here, equation 8. And in this case, you can see there is a variance tau. So that's why we need finite second moment. And again, if we take, for example, a small masses m, and as I said, expectation of tau should be of order n in this case. And if, for example, we take exponentially distributed time between collisions, then if expectation of tau of order m, then the variance of tau will be of order m squared. So it means that this variance will be of order m squared, and the whole expression here will be m squared divided by m, so it will be of order m, which is small. So in this case, we can see that like even if this time is random, then we still can construct this model which will be asymptotically equivalent. Okay. So, but here we have considered two cases. In both cases, the external force was constant. Now we want to consider a time-dependent increasing force f of t. So if now f of t is our function f of xt depend on t, and if this function goes to infinity when t goes to infinity, and also we need this expression that
in previous slide you consider tau exponentially distributed or any distributed with second moment.
No, like in the original theorem here, we consider like any distribution with finite second moment. But this is just an example. If we take, for example, exponential distributed, then in this case, variance will be of order m squared. And in this case, this one will be of order m, which is small. So this is just an example. But in general, we can take like any positive random variables with finite second moment.
But why m is or smaller one? It is again example. What is it?
It is again example, yes, because like in original, it is just enough to consider m is less than 1 to have this property. But this is in future theorems we want to understand not only asymptotically equivalent, but equivalence in some bounded time. So if trajectories of two models will be close to each other, but if we want to make this, then we should take, of course, masses should be small and time between collisions should be small as well. That's why I'm talking like here, like specific case when m is small. But in theorem, so it's okay. It works in asymptotical equivalence. It works without n. So the only condition here is that m should be less than 1.
But is m is small, then by this last equation, the variance of the v is very large because v left hand side, because m is in the denominator. M is divided.
Exactly. But in this case, variance of tau will be small also.
Yes, tau.
If we take exponentially, for example, exponentially distributed, because like expectation of tau should be of this form, right? And this one is of order m. And if m is small, then this one should be small, and it means that we have exponentially distributed random variable with this mean value. Mean value is small for this exponential, but variance will be even more small because variance will be of order m squared for exponential.
Thank you.
Yeah, so in this case, for exponential, if we take really small m, so everything will be okay. And now if we consider force which is depend on t, and again, we like take some uniform bound for velocities of second particles, and we take time between collisions, which is constant, and we have the following properties. Actually here, like function f converges to infinity when t goes to infinity, but it doesn't converge very fast. For example, f, like according to these properties, f capital could be some exponential function, which is exponentially depend on exponent of some function which is linearly dependent on t. For example,
and previously w again was bounded, or it was not.
In previously w was bounded by this constant, yes.
Okay.
But in this case, it is bounded by some constant, and this constant is actually doesn't matter because we will see that the answer will not depend on these quantities wn in the next theory. So this is just some constant, some uniform bound, but yeah, and that's it. Okay, so for example, here f could be some exponent, or f could be some polynomial function. So these properties will satisfy here. Okay, so if we have such a function f.
Excuse me,
Yes.
Vasily. How it could be that wn sequence is bounded? Wn is force divided by a, yes?
No.
W, this is just velocities of other particles. They could be like whatever we want.
Velocities of external particles.
External particles, exactly. But for previous theorem, we should bound it by f over a, because otherwise this quantity will be negative. But the time between collisions could not be negative in this case.
Okay, thank you.
So yes, this is just velocities of external particles. Okay, and here we have theorem that if we take masses of external particles the same, it is equal to m, then and also if we have this equation for masses m and tau, then for any initial conditions, velocities in model with friction, model with collision satisfies the following inequality 10. So of course this velocity is bounded by 1, but the lower bound bounded by 1 minus 2m over 1 plus m. And in this case, you can see that if we take a small parameter tau, so if the time between collision is small, then by this equality 9, if tau is small, it means that m will be again of order tau. So in this case, this lower bound, this fraction here will converge to 0. So in this case, we have like again asymptotic equivalence of v and v tilde. And yes, and actually this bound 12 goes from this equality 9, if we just consider, because this one will be 1 minus 8 tau plus something which is of order tau squared. So when tau goes to 0, we have the following things, and here we have again asymptotically equivalence. Okay, what is interesting is that we with two models, when we have constant force F, or we have a force which is depend on time t, then we have the following expression for tau and m. But if for small m, and if you remember, then at this time dependent force f of t goes to infinity when t goes to infinity. And for example, if in the first model, if this constant f goes to infinity, then this term will disappear, and it will be only 2m over a times 1 minus m. But if m is small, this one is 1. So like the main term will be tau should be equal to m over a plus something of order m squared.
What is a?
A this is a very first parameter for friction force. In our differential equation, we have minus AV, minus A times V. So this is just A, this is parameter for friction force. And so this A goes from friction model, and this masses M and tau, they goes from model with collisions. And we have like this for small masses M, we have this equation, which works both for constant force, for deterministic collisions, or for random collisions. Yeah, for random it should be, yeah, I should take here expectation. But I mean, we have like the same equality for both models. So tau should be 2m over a. Okay, so we have considered force constant, force when it depends on time t. Now we want to consider this force. What if it depends on space x? And in particular, we're interested in Coulomb potential. So this is Coulomb potential. So it means that like at the origin there is a really huge object which attracts our main particle to 0. Okay, so for model. Yes, for this is model with friction, with this particular force Coulomb potential, and here we need the auxiliary lemma, which called. So this is just a lemma. Then there exists some time t, which is a supremum of t when x of t is greater than delta, like because there is a really huge force which attracts our particle, then it will eventually go to 0 Actually, this time is finite and strictly positive, and also for all t, which is between 0 and capital T, it holds that both trajectory x of t and the velocity of particle, both these trajectories are uniformly bounded. So according to this lemma, if we have this condition, so x of t and v of t, they're uniformly bounded, we want to construct to find properties when this model will be equivalent, but not in asymptotical case. So not when t goes to infinity, but in this when t between 0 and capital T, and when time between collisions is small. So here we have the following theorem. So we have Coulomb potential. The moment, the time between collisions is equal to tau, which is constant. And in this case, again, we take the same masses. And also, in this case, we need that the velocities of the other particles should be of order tau. So no more than of order tau, because in this case, we want that trajectories should be close to each other. And in this case, if we have the following equation 17, which is, again, you can see like the same form as it was before, the dependence tau on A and M. So if we have this, then trajectories like Chebyshev norm between model with friction and model with collisions, this Chebyshev norm is of order tau. And velocities are the same. So velocities are close to each other as well, as tau goes to 0. So here, like, it is more interesting because, as I said, we don't have asymptotical equivalence. We have equivalence during the finite time between 0 and capital T. And even in this case, we have the same equality for tau, M, and A. Okay, and another question. Okay, here we had moments of time tau, which is constant, but what if we take random tau in this case? Okay, if we take random, then in this case we need to take the support of tau should be like bounded by support of tau n should be bounded by constant c and constant tau, and this constant tau will go to 0. So in this case, we are not allowed, for example, take exponential distribution, because exponential is not bounded distribution. And in this case, it could be sometimes then this exponential time will be like really big. And in this case, our trajectories for two models, they will be like in a big distance. So we are not allowed to use, for example, exponential distribution, or as before, like only have if they only have finite variance. In this case, we really need that this time will be supported in some interval which is goes to 0 as well. And in this case, yes, in both models, trajectories for x and for velocity in L2 norm will be close to each other and of order square root of tau. So, and actually, in these theorems, in the last two theorems, we used f of x, which was the Coulomb potential, but the only fact we use that during this time 0 and capital T, we know for sure that x and the velocity will be bounded. So actually, if we have like smooth enough force F, we could prove like the same result also. Okay, and yes, that was all what I wanted to say. So, and I'd like to say thank you very much for your attention.
Sorry, I don't understand one point. You consider two different systems, one with collisions, another with friction, yes?
Yes.
How it is possible, what in this theorem and the previous, that not for large t, but even for small t, after one collision or before one collision, these trajectories are close. How it is possible? The collision of different systems, one with friction, another without friction. For small t, how is possible?
Because the time between collisions is equal to tau, and tau it is really small, so tau converges to 0. So I mean, if time is small tau, then the trajectories will diverge from each other no more than of order tau.
No more
time
than
between
tau.
collisions,
Okay.
the time between collisions also small. Of course, in general, if time between collisions some constant, of course it is not true. Yes.
Okay, thank you. Understand. Thank you. Thank you.
If I'm truly understand the random time situation, but constant f, the situation when this variance is so this formula 8 becomes constant, it's exactly Poisson situation, is it? Because I think it's natural to have a Poisson distribution for time between collisions. I think it occurs in many physical models, and it is exactly a situation when it goes to the finite limit. I mean, if expectation is small and variance is of the same order, the m cancelled. So is it true?
But for Poisson case, so the time, like if we take Poisson process, the time between occurrence is exponentially distributed, right? And in this case, we have
I say you distribute times by themselves.
by themselves
In Poisson distribution.
Yeah, in this case, it will go for the m, and m cancels. Yes, and it will be like constant. Yeah.
So Poisson case for time is exactly the case when it's fine. So we have not divergence and not so for small expectation. Yes.
Yes. Yes.
Okay, I think because it's interesting, because Poisson is very usual, very specific distribution in many cases. Okay, thank you.
Yeah.
This L2 norm, this 8 bound, it will be for the constant, so it's not so good. It is better to have it going to 0. Therefore, exponential in this case better.
In this case, yes. Yes, because exponential of order variance of order m squared.
Vasilii, I have a question. We have two models with friction and with collision, yes?
Mm-hmm.
Is it correct that we take, for example, model with collision, with some parameters, with masses, the time between collisions, fixed or random, whatever.
Mm-hmm.
Is it true that for every such model, we can find system with dissipation, with some dissipation parameter, or no?
Yes, exactly. So because we have like this, like the same picture, like for all our theorems. So like mostly we have, for example, let's say this expression here, or like, okay, let's say this one. This is the equation 30. So we have the following expression, and let's say if we have like small, like time between collisions is small tau. Mass is also small. So in this case, it is enough to take A, the parameter for friction, which is 2m over tau.
Mm-hmm.
So
But-
that's we can rewrite this equation just to find what is A, what's the
To
parameter.
find the dissipation parameter. Okay,
Yes,
thank you.
exactly.
But whereas value of the force, it is independent of the force. This
Not really. So in this case, of course, I mean, when the force is constant, we have the following expression here, and in this case, it's more complicated. But when, for example, let's say in this case, when W is equal to 0, then we have like the same expression. So like almost, and in the other cases, when we have considered even this force, which is dependent on X, we got the same expression. So even, I mean, for almost like all forces, which is like smooth enough, even if this force goes to infinity. So for, I mean, one case is asymptotical case, another case is in some finite interval. But in both cases, we have the same like expression for A and tau and M. So if we have collisions, which is when time between collisions tau is really small, and masses of particles are of the same order as this time between collisions, then from this equation, for example, we could find parameter A, and it will be the model with friction.